All right, let's look at 710, dissipative interactions. We've seen non-dissipative interactions. That's interactions between an object and, say, a spring, and an object and, say, the earth. Okay? We can, in non-dissipative interactions, we can store the energy. It's reversible. What does a reversible mean? Means that if I throw an object up, because of the non-dissipative interaction between the object and earth, the higher it goes, the more you are really storing energy, and then you can regain that energy. You can convert that energy into kinetic energy, or this object pushes against the spring. As the spring deforms, right, you're storing energy in the spring, which you can use again later. So this is non-dissipative, reversible energy. However, now we're looking at dissipative interactions where we can't store the energy, and it's not a reversible process. So, sorry that I meant to show this. This is reversible. You squash the spring and then it can reverse back to what it was. You throw the object up, it comes down. It's a reversible process, a reversible interaction. Whereas what happens if you have a puck sliding across a floor? Well, we know that it starts off with a high kinetic energy, or a certain amount of kinetic energy. And as it's sliding, the kinetic energy is obviously decreasing because of the friction slowing it down, and the thermal energy is increasing. Okay, and then it finally comes to a halt. The kinetic energy is zero, and the thermal energy is at a maximum. Okay, but this is not reversible. We don't suddenly see this puck begin to move backwards spontaneously. There's a word here, spontaneously. It doesn't spontaneously begin to move backwards. Okay, so it says we could never observe a puck start to move on its own, spontaneously converting the incoherent thermal energy. Remember, this thermal energy is incoherent. Okay, we can't observe it spontaneously converting incoherent energy back to coherent kinetic energy. So we can't see this automatically happen. Okay, so it's an irreversible process. So I like this. This is kind of the mother of all energy equations. Okay, so for a system that's closed, okay, meaning no energy is being transferred to or from it, we know that this is our general equation. The total change in energy is made up of these four different energy types: delta K, delta U, delta source energy, and delta thermal energy, and that should equal zero. Now let's analyze this situation, which is what you should do for every problem. You should always come here and say, okay, what types of energy are we looking at? Well, we've got kinetic energy, yes. So yes, we've got kinetic energy. Are we considering the change in potential energy? No, because it's going horizontally, it's moving horizontally. So we're not going to consider potential energy in this one. There could be cases where there is potential energy, but not in this case. What about source energy? Is there any nuclear energy, any chemical reaction, nuclear reaction? No, there isn't. So we're left with these two guys. In this specific case, we're left with kinetic and thermal, and the kinetic energy is being converted into thermal energy. Okay? All right, so this is just another way of rewriting it. And that is it. Actually, this always holds, even in elastic, inelastic, and totally inelastic collisions. All we know is that in an elastic collision, your thermal energy would actually be zero. Okay. Nevertheless, look at it from this perspective, try to understand it from here, and then apply it to every specific case. Okay, see you on the next one.